Hello, our project is hand-drawn sketch recognition using several machine learning models. KNN is a simple non-parametric machine learning algorithm that classifies data points based on the majority class of their k nearest neighbors in the feature space. Using distance metrics like Euclidean distance, it's intuitive, effective for small datasets and requires no training phase. For our project, we explored three feature extraction methods: HOG with PCA, CNN, and CNN with PCA. Among them, CNN combined with PCA achieved the best performance with an accuracy of 41.54%, followed by CNN alone at 39.88%. We designed a feed-forward ANN model with an input layer of 2048 neurons followed by two hidden layers with 512 and 256 neurons respectively, both using the ReLU function to introduce nonlinearity. The output layer has 250 neurons, each representing a class with softmax activation to generate class probabilities. For training, we used a cross-entropy loss function to measure prediction error and optimize the model using gradient descent. We trained the model for 60 epochs and a batch size of 64 and a learning rate of 0.005. We got an accuracy of texting as 56.13%.
One of the model we used was logistic regression. Today I would like to explain how we use logistic regression in our hand-run sketch recognition project. Unlike binary logistic regression, which predicts between two classes, our multivariate approach handles multiple classes simultaneously. Essentially, this model uses several input features extracted from sketch to compute a probability distribution. In this dataset, we have overall all 250 possible categories. Each feature contributes to a weighted sum, and then the model applies a softmax function converting these sums into probabilities. The class with the highest probability becomes the prediction. During training, we update these weights using gradient descent, minimizing the cross entropy loss. This interactive process helps the model learn the optimal set of weights by reducing the prediction error over numerous efforts.
I combine deep learning and statistical methods by using multivariate Gaussian classifier on feature extracted from image using CNN. Since the data had many dimensions, I applied PCA to reduce noise while keeping important information. The classifier trees each class has a multivariate normal distribution, learning the average and spread of the each class. It makes predictions by calculating which class the data is most likely to belong to based on the probability. Even though the model is simple, it is good. It gives good results, showing that traditional generative models can still work when all used with the deep learning features. This project helped me better understanding how probability classification and PCA model regulation works. I'm giving a short overview of my project where I built one versus rest linear SVM classifier multi-class image classification using deep learning features. I use feature extraction from image using convolution neural network and feed them into a custom one versus rest model using crit-len linear SVC. For each class, I trained a separate binary classifier and during friction, the class with highest score was chosen. I trained the model on a well-balanced dataset and achieved good test accuracy. This shows the traditional machine learning methods, when combined with the deep learning features, can still perform very well even on complex tasks.
A decision tree classifier is a supervised learning algorithm. The model was trained on labeled sketch data and tested for accuracy. The results showed only around 11% accuracy, which is just slightly above random guessing for a 10th class classification problem. This low performance suggests that the representation of sketches, when fed directly into a decision tree, is too noisy and high dimensional for the model to effectively generalize. And next, we turn to k-means clustering, an unsupervised method to group similar sketches without using labels. After applying k-means and comparing the clusters with actual digit labels, the clustering accuracy was also around 10%, indicating that the clusters did not align well with the true classes. This result highlights the difficulty of using simple clustering image data, where a high intraclass variability and interclass similarity can confuse the algorithm.